Alright, so today we're going to go over how to log data with the MPVI Standard, aka the non-pro version, and how to get data into your scanner and to be able to tune your car. Alright, so we're just going to go over how to add inputs to the PCM. So we're going to how to get things into the PCM, the transforms, the map parameters, we'll talk about Lambda some, and then we're going to talk about other sensors as well. So that's going to be how we cover today. I'm not going to actually show how to wire this in. I'm going to assume that you've already done this, and we're going to go from there. Alright, to get things into the PCM, we're going to go with using an unused sensor. So any 5-volt sensor that we're not using. Typically, a lot of people aren't using the EGR or the AC pressure sensor on high performance cars because we've already either deleted it or done something along those lines, but the input's still there and we can still use it. So there's other things you could use here, but these are the two most popular by far. So the second thing we're going to do, wire the sensor in, obviously, so that way the PCM is reading the voltage from the sensor. That's the whole point. So it's reading the outputs from the sensor and into the PCM. From there we set up a scanner to monitor that channel in the PID list, aka the EGR or the AC pressure sensor, etc. Alright, so first thing we need to do is add the input for whatever sensor we're using, be it the EGR or the AC pressure sensor. So we're just going to click the little gear. We're going to go ahead and add the EGR in here. So we're just typing EGR, and we can go down to find the EGR voltage, and right here you'll see EGR sensor, and this is the sensor itself and the voltage range. So that's the one we want right here. Alternatively, it could be the AC pressure, so we can try that one. We can go with the AC pressure sensor voltage. Just type in AC space, it'll come right up. So AC pressure sensor here, voltage, so this would be another one you could use. And again, there's more available inputs out there. You can be creative with this, but here's the two that most people use right here. So now we have those into the scanner. We can go ahead and use these as our transform function, and we'll cover that here in a sec. Alright, so transforms are just math functions that are going to convert whatever the voltage is into usable data. So we're just going to convert it into what it needs to look like in the scanner, basically using a little bit of math. It's actually fairly easy. So that it's going to tell us basically what each volt is equal to X amount on whatever sensor we're using. This applies to any sensor, including widebands, field pressure, trans pressure, anything that can log this. Basically, we're going to get a linear value, and that's pretty simple by figuring out the range of the sensor. And then, of course, we need the voltage range as well. And this voltage range, that's how we're going to get the linear value. Now, to get the offset, it's typically it's going to be, on most gauges, it's going to be the 0 value, but that doesn't apply to everything. I'll show you a little bit different offsets on different sensors, but this is what we use to get it to match the gauge. So that's basically all the offset is, where this value needs to start, essentially. Alright, here's an example of a data sheet from a particular sensor. So this is a wideband in this case, so we can look at 0.5 volt analog inputs on the right here, and we can see our voltage. It goes from 0.5 up to 4.5. So this is a 4 volt range, and this is what we're going to use to actually come up with a transform using a little bit of math. We plug in and can actually turn this into a usable formula in our scanner, and that's how we're going to convert it to an input. So we'll go over that here in a sec. Alright, so the generally used one here is to find AFR is pretty simple. Is we're going to take our voltage input, we're going to divide that by linear, add the offset to it. And then the offset, again, this is just to get it to match the gauge. So this is what we convert. The linear value is essentially the value per volt. So that's what we're going to come up with here. So that's equals the highest voltage minus the lowest voltage, which gives us the voltage range, divided by the AFR range, which is the highest minus lowest, and it's going to give us a denominator here we're going to use to convert the signal into something we can use. So these are made up numbers, but let's imagine our gauge in question has a 4.8 high voltage reading where it's accurate, minus the 0.4 volts. So we're going to take the value of this and we're divided by the total AFR range, and we're going to get a denominator, aka a linear value of 0.444, and the offset will just be simply the lowest setting on the gauge. So add the lowest AFR, just add to it, and that'll give us it'll match the gauge. Now this is what you would adjust if the reading does not match. you change this. So if it doesn't quite match, you alter the offset until it does match. That's how you get that to match. But the completed formula would be simply voltage divided by 0.444 plus 9.8. So let's take a look at what that looks like in the scanner, and we'll plug that in. Alright, so now we actually have to get this EGR sensor voltage converted into something useful. So first thing we're going to do is go ahead and go to Tools. We're going to open Math Parameters. We're going to open this up and we're going to go down and select our first open math parameter. In my case, it's 29th one. I know I got a lot in here, so we're just going to go ahead and make this one EGR wideband 4. Abbreviations EGR wideband. No, it's going to be EGR voltage divided by the linear, or aka the that's going to be the total AFR per volt. We're going to add the offset to that, and so that's going to be the lowest setting on the chart, and then we're going to go ahead and plug that in, figure out what these are. We need to convert and figure that out. So new variable, we're going to go ahead and go with the EGR sensor. Obviously we need to add this in because that's what we're looking at. That's what we're actually logging. So we need to take the EGR sensor, select it, and we're going to leave it in volts. We're going to say OK. Alright, now we need to divide that by the linear value. So we'll put this in brackets or parentheses because it's going to matter later. We'll go ahead and divide that by what we need to figure out. So I'll open the table. And here we go. We got this is for AEM UGO. So if we see our voltage range is 0 to 499. So we're just going to use 5 as the. We're going to start with 5, and we need to figure out the total range. So we see 10 to 20, essentially. So the decimals that small aren't going to matter too much here. So we're going to go ahead and just go 5 divided by 10, which is the difference between the total range. So we get a voltage range of 10. 5 divided by 10, it's going to give us 0.5. And we'll prove that real quick. So we go 5 divided by 10, and we should get 0.5. There we go, 0.5, and that'll be our, just to show the difference. So we go back to our scanner, and we're going to use 0.5. So we just divide by 0.5. And for you math whizzes out there, that is exactly the same as times 2. Either one works, so you can use either one. So 0.5. And we're going to add the lowest setting on the gauge, which in this case was 10. So for gasoline AFR, we're dealing with AFR right now. We're going to go 10, so we're going to just add 10 to that. So we'll add 10. Okay, so that will give us our raw conversion directly to AFR that the gauge is reading. Now, if this does not match the gauge, what we change is this number here. This is the number that we alter to get it to match the gauge. So in some cases you might see something like this, 9.8, whatever that may be, to get it to match exactly what it says on the gauge. It might be off a point or two. So, but in this case, just when we're getting started, we'll go ahead and use 10, and then just watch the gauge and what the scanner says and get them to line up. If we have to change it, that's the number you change right there. Alright, so now that we have our raw data plugged in, so this is going to convert it to a raw number. So this one we're going to make sure that we're matched up with the gauge. So we can go ahead and copy this. We'll go ahead and copy it, and we'll go down to another one, and we'll open that up. And then we'll go EGR wideband error, and then we'll use it same thing. And this is going to be error from commanded, so we need to actually plug all this in. I'll go back and grab the English version up here, and we'll have the error down here. So what we're going to do here is multiply this by the formula shown earlier. We're going to multiply that by 100. We're going to have to add another 2 sets of parentheses on the left because we have to put this into a parenthesis as well. So we go ahead and, because we have to subtract the commanded, and we have to throw that into a parenthesis, so all that has to be solved first. Then we go divide that by commanded again, and that will give us an error percent from commanded. So what we're going to do is go ahead and add these in down here. So first thing we got to do is multiply by 100, and we add the 2 sets of parentheses on the left, to build the formula because there's going to end up being 3 on the right. So we go ahead and parentheses that in, subtract commanded from that. So first thing we have to add a new variable. We're just going to go AFR commanded, and we'll see right here, air fuel ratio commanded. Select that, say yes, sounds good. So we're just going to use the generic sensor for AFR commanded. There's a couple of these you could use. This one will work just fine. We'll add that in. It's 5121, pretty common to use. We have to throw that into parentheses because we're subtracting it, so that won't occur unless we put it into parentheses. So we have to make sure we have 1, 2, 3 on the left, 1, 2, 3 on the right. So now we can divide that by commanded again. So it's going to be the same one again. Select it again. So yes, sounds good. Use the generic. Yep, okay. And now we see that it's pinked out down here. So now we need to make sure we're logging that in the channels list, because that's why it's highlighted. So we'll go ahead over here. We'll right click. We'll add a channel. Say AFR commanded, and we go ahead and select that one, whichever, and it should pop right up. And we see our go back to our math parameters. Make sure that we're logging the correct thing. And there we go. And I see that the sensor is now highlighted. It will log our percentage of error along whatever we want to plot that on. So from here we just use that input as our thing. So we add a graph. We can just go ahead and we'll go O2 AFR error, and we see that it's basically set up. This is a stock or default one, but I'm just going to use it just to show what you do here with that input. So we'll add a table. Actually, now we'll clone this table, and we'll go ahead and just change this to AFR error up here, and we'll go down to what we just built, user defined. Go down and find that one, AFR error, select it, and now we'll select decimals as you want. Cell hits, we'll set it to like 50, like usual, high, low, 20 or 30, whichever one you want to use. You should pick your colors, and there we go. So let's take a default table, turn it into our wideband AFR table. And of course you have to build it from the scanner, plug in the correct numbers, values, everything else. I'm not going to cover that right now. I'm just showing how to log the actual error now that we're using from our wideband, and now it should plot right along whatever axes we want, and on the graph we want. So that's how we're going to use that math that we just made. Alright, so AFR versus Lambda, real quick. So the math parameters, we'll have a little bit of variance here. Because the lambda is just going to be a 1 and going to vary probably like 0.5 to 1.5. What this means is basically it's the stoichiometric ratio of 14.7. If that's used, a lambda of 1 would be 14.7 if that's the EQ ratio. Whereas if it was 0.5, it would be half that, and if it was double, then it would be double that. So that's something to keep in mind. That's quite different, but however does work a lot better with other fuel types, because if you just use the value 1, whatever that stoichiometric ratio is will be 1, and whatever ratios off of that are your lambda values. So it's less numbers to remember at the end of the day as to what to set everything to. So we'll go through how to set this up here in a sec. Alright, so let's take a look at lambda, or aka the EQ ratio. So if we're going to do it this way, it's actually the same formula. So we're going to do the voltage input divided by the linear, and we're going to add the offset. The linear value is going to equal the same voltage range minus the EQ range. So in this case, it's going to be, we're going to use a little bit different math. So we're going to have 4.8 minus 0.8, and that's going to give us 4 volt range. We're going to divide that by the range of the sensor. So this is going to end up being a 6.25 value for our linear, and the offset will be the lowest lambda that it can go, so that would be 580 in this case. Completed formula would look like this: voltage divided by 6.25, added, then you add in the lowest, which is 580, so it's going to change what our scanner looks like slightly. Go take a look at what that would look like here in a sec. Alright, so adding lambda is pretty much the exact same thing that we did with the AFR version, but this time we're going to use a little bit different numbers. Just to go through this. So I've already cleared these out, so but we still know the formula is the EGR voltage minus divided by the linear plus offset. So let's go ahead and plug in the numbers and figure out what we get using a data sheet, the same one again. So this one again, 5 volt range, but we also see lambda listed here, so we're going to go ahead and we know it's 5 volts, so we'll take 5 and we'll divide that by the range. So we're going to go ahead and throw a parenthesis in here. We got 1.365. We'll just figure this out real quick. Subtracted from 0.683. 0.683. The other parenthesis in and hit the equals, and we're going to get 7.331 as our value here. So we're going to go ahead and go back to the scanner. We'll go ahead and enter that in. Again, we're using the EGR in this case. So we'll scroll down to the EGR, sensor voltage like we had before, and we'll leave that in voltage. We'll divide that by 7.331, I think it was. Check that. Yep, 7.331, and we'll throw that into parentheses real quick. And then we're going to add the lowest value, which was 0.683. So we'll go ahead and put that in here, plus 0.683. And now we have a raw conversion, and then we'll check this off our gauge and adjust as needed on the offset right here, this value, until it matches. Now, to turn this into commanded is the exact same thing. So we copy it, we're going to go down to the error, we'll paste it in here, and again we have to do the same math. So we'll do 100 multiplied by that, and we need the 2 parentheses on the left because we're going to end up with 3 on the right. So we got 1 there, we've got to subtract. Instead of commanded this time, we're going to use EQ ratio. So we have an EQ commanded here. Yep, sounds good. Commanded lambda. Okay. Subtract that, and then throw that into a parenthesis as well, and then divide by, once again, EQ again. Will give us the lambda error in percent. So that gives us a percent error from lambda, and that's how you turn your EQ ratio into a correction. So that's pretty much it right there. And so no real change from the other way. It's just slightly different numbers. So there's other sensors out there we can use to get into our scanners, again through the EGR or various other points. We can use fuel pressure, transmission pressure, any gauge that puts out an analog input of 5 volts basically can be logged using this manner. Pretty handy little feature. Alright, so I'm going to use fuel pressure as a conversion example here. So it's still going to be pretty much the exact same math, except for a few little differences to get the offset right. Because in this case, we're actually going to subtract it in the example I'm going to use. So input voltage going to be divided by the linear, and this time we're going to subtract the offset. The linear is equal to the voltage range divided by the pressure range as before. So in this case, we're going to get a 0.04 after this, because it's going to move the decimal over on 4 volts. Offset is going to be the minimum voltage divided by the linear to get the offset, because this one goes 0.5 volts is equal to 0 in the example I'm going to use. So in this case, we're going to use 4.5 minus 0.5 divided by 100 psi, subtracted from, and then subtracting the 0.5 divided by 0.4, which is going to actually give us 12.5 on the fuel pressure. Take a look at what that looks like from the chart here in a sec. Alright, so let's take a look at this. So we're going to use this example, so 0 to 100 psi gauge. So we'll use this one here, and we're going to use the range, which is 100, so 100 to 0. Again, this column is what we're looking at, so that'll be that one. So let's go ahead and pull up the calculator, and let's figure this out. So let's plug it in. We have a voltage range is 4.5 down to 0.5. So we have 0.5, 4.5, and we don't need a calculator to know that's 4 volts in difference. So we know that's 4. So we're going to clear this, take 4, and we're going to divide that by the total range. And honestly, you don't really need a calculator for this either, but we know that's going to turn into 0.04 from 100 down to 0. So 0.04 is our multiplier here, or actually in this case the denominator. So we're going to clear it. So we know 0.04 because we're going to divide into these numbers. So let's take an example here, and we're going to take 2.5 and we're going to see what that looks like. 2.5, we're going to divide that by 0.04 and we'll get 62.5, and as we see, that's wrong. So how do we get the offset? We see that there's a difference here, so let's just take a look at how to get the offset. So we look at 0.5 and we know our denominator is 0.04, so let's see what that looks like. 0.5 divided by 0.04 turns into 12.5. Now if I take 50 and I add 12.5 to it, I've got this exact same number I just had. So let's take a look at that one more time. So now we know it's 12.5. We got to subtract off 2.5 divided by 0.04, 62.5, subtract the 12.5, and we get our answer right here. So that's what we get, 50. So that's what it's reading. So that's how you convert basically any gauge using the data. So if you have to figure out the offset, divide the denominator by the min voltage and you should get the offset. So that's going to give you the offset value you use, and that would work when we could log our fuel pressure using that method. It's basically in conclusion here, any analog 5-volt sensor can be logged using the correct math function so long as it's a PCM input. So again, there's various things. Typically the GR AC pressure, very common to use. And this math applies to any linear style sensor. That means any sensor that has a voltage range and a linear value to said voltage ranges, and it goes in a straight line, then this could be used. So offsets are, and again, offsets are adjustable in all cases to match the gauge versus scanner readout. So if you've got an error, don't adjust the linear value, adjust the offset. Because if you adjust the linear, it's going to change the whole dynamic of where that's going to end up. So adjust the offset to get it to match the gauge, and then everything else should be right. So that's pretty much it. I hope you guys enjoyed the video, and if you have any questions, feel free to comment below or find me on HP Tuners or LS1 Tech, and I'll see you out there.